Hey everyone, welcome to another episode of the Whiteboard session. And today we have with us Jordi, co-founder of Polygon, and we're going to talk about Polygon zkEVM today. Jordi, do you want to talk a bit about yourself and Polygon zkEVM?
Yeah, well, I'm Jordi Baylina. I'm the technical lead at Polygon zkEVM. Mainly what I've been doing for the last 3 years now is the Polygon zkEVM. So that's what I expect you to ask me.
Exactly. So actually, I believe 3 years ago, many people, including some of the prominent zk researchers, don't believe that we can have zkEVM in a few years, and Jordi, you proved them wrong.
Yeah, I mean, I didn't believe it either. So when we started, this was a kind of a dream. Actually, the story was that Barry Whitehat from the Ethereum Foundation, he convinced me. Actually, we're like spending a couple of months in my home, just in the whiteboard, just trying to figure out what were the stoppers for building that. And we were like solving all the concrete details, small details, and at some point say, okay, this is super complex, but this is theoretically possible. And it was from there that we just start building. And for the last 2 years has been also a journey of solving challenges, a lot of challenges, and until we got to the point. So yeah, that's an engineering process, I would say.
Right. Actually, I'm curious from your point of view, what are the major obstacles back in 2020? Like from when you first started, what do you think are the major bottlenecks?
Well, the technology that we started with was was the normal zk technology. Was very much. I like to talk about the simile between electronics and circuits. I mean, this is not electronic circuits. We are not talking about transistors. We are talking about polynomials.
Right.
But from the mindset, so designing circuit. I mean, we call it circuits. Designing zk circuits and designing electronic circuits has a lot of similarities. So that's why we like to talk.
Right.
And at that point, we were like if we were designing circuits without a clock. So that means that okay, you can build any computation. At the end, you have ands and ors. Okay, so here you can do whatever you want, but the quantity of ands and ors that you need to do for something specific is huge. Especially if you want to do ifs. I mean, if you want to do conditional things, and in zkEVM you have a lot of conditions. Depending on the transaction, you will execute one opcode or the other, and there is a lot of conditional things. So doing a generic EVM was like impossible, and you count the number of constraints, and it's like a huge number there. And here the big invention was like inventing the clock. I mean, inventing the clock was very much this concept of a state machine. These Starks are very good because it comes very naturally. And at the moment that you have a state transition function, I mean, at the moment that you have this kind of a clock, then you can build a processor. And if you can build a processor, then doing conditionals and generic programs are easy. And this is very much the strategy that we follow. I mean, we built a processor. We built a processor with polynomials, not with transistors, but we built a processor. We built an assembly on that processor, and we built a program that's running that processor that mainly what it does is interprets the EVM. This was the full strategy. This was and this was proven the right way to go. This was the biggest part, and from there we can talk about different challenges. I mean, the memory, HX, ECDSA, or even pairings recently. Or I mean, we can even arithmetic operations, for example, is a challenge for itself, or how we do the storage, or I mean, each of the state machines is a challenge. By itself, but this technology has been proven that you can do whatever you want. It's like having transistors. I mean, if you get the transistor, of course, you need to build the processors, but you can build whatever you want.
Okay, maybe let's start from there. Like maybe we can talk about how the state machine works and how the analogy between the regular CPU and the zk processor actually works. So maybe we can start with the different state machines that you build, and then we can talk about how that relates to the EVM.
Yeah, the idea is that we can I mean, what's the idea is imagine a state machine. But you can imagine any state machine, but probably the easiest state machine to think about is the Fibonacci. Fibonacci you can read as a state machine, but at the end is like you have two states. Okay, so we may say this is state A and B. Okay, and then okay, what's the next step? What's the next step? Well, the next if I plus 1 is equal with A plus B. Okay, and if you want B I plus 1, maybe it's equal to A. Okay, it's a state machine. I mean, you are just this is the state transition function. Of course, you have maybe an initial state, but you have a state transition function, and you can do that as many times as you want. You can do multiplication. Actually, you can build a processor. I mean, this is a state machine. Okay? So here the way it's built. So how we convert that to a polynomial thing. Okay, so this is the problem. Okay, let me explain first how a polynomial commitment works, because I think it's quite easy, and then we try to join the both pieces together. Okay, so when we have a polynomial, I mean polynomial, when we're talking about polynomials, but a polynomial you can understand as an array of values. Okay, if you have and mainly we call it this in the evaluation form. For example, you have a straight line. This is a polynomial of degree 1, and you have two evaluations. For example, if you have the evaluation at 0 and 1, you have maybe this is I don't know 43, and here you have 31. Okay, so this is a straight line. So this is a polynomial f of x equals to ax plus b. Okay, so you can, I mean, you have a polynomial, but with these two evaluations, with 31, and you can express this as 43 and 31. Okay, this is what we call it. This the polynomial expressed in evaluation form. This is for a degree 1, but you can do that with degree 1 million. Okay, that's a degree 1 million. You with 1,000,001 values, you get the definition of that polynomial. Okay, this is the, I mean, this AB, whatever it is. I mean, whatever numbers are there. Here would be the coefficients. This would be the coefficients expression. Okay, and this is the evaluations expression. In this case, this is like a vector. In this case, the base of this would be 1x or even x squared, x to the 3, okay? And in this case, the base would be the Lagrange polynomial 1, the Lagrange polynomial 2, Lagrange polynomial 3, and so on. Lagrange polynomials is a polynomial such that at the Lagrange 1, at 1 this is 1, and in the other points is 0, and so on, okay? But this is just the same way of expressing a polynomial, okay? So the schema that we have when we do a polynomial is, okay, the idea is we have a prover and we have a verifier. Okay, prover in general is called Peggy. Okay, and the verifier is Victor. Okay, so this is, I mean, we can find this. Okay, this is Victor.
Okay,
and this is Peggy. Okay.
Okay.
So the idea is, so what's the polynomial commitment schema? So how it works? Well, so Peggy just think about the polynomial, for example, this one, okay? He commits to this polynomial f of x, the full polynomial. One way to thinking about committing the polynomial is, I mean, it's hashing the polynomial, okay? Commit is in general is a hash. We'll see that it's a special hash, but it's a kind of a hashing of itself, okay? So if we are here, if we are thinking in finite fields, here we, instead of in reals, we are talking in finite fields. One way of hashing a polynomial, it's a very unpractical way, but one way to think about is, okay, you can take all the possible values. It's a finite field, so you have like all of them. You see how evaluates to all them, and then you just create a Merkle tree of all that, okay? And then you just create a, this would be, I mean, this uniquely will generate a hash. I mean, this is not practical, but for thinking, it's a way of thinking this polynomial commitment there, okay? So I commit to a polynomial, okay? And in this case, Peggy just sends a random number z, okay? And Peggy just sends it sends f of z. It is a concrete number, and he sends f of z, but it also sends a kind of a proof that f of z is matches to this polynomial. Okay. In this case, the proof in the case that I explained you before would be the proof would be the Merkle path of this polynomial. Of course, this is not practical. Okay, but this schema. I mean, there are different methods of doing this, but this is perfectly possible.
Right.
Okay. This is a polynomial commitment schema. Okay, but imagine that imagine that instead of working with one polynomial, I want to work with two polynomials or three polynomials. Okay, so imagine they have f of x and g of x. Here I can send commitment of f of x, g of x, maybe the h of x. Okay, so I can send you three commitments. Okay, and here I want to prove you that this has some relationship. For example, imagine that I want to prove that f of x is equal to g of x plus h of x. Okay. Well, the thing is that a way to do it. Okay, I send you the three commitments. You send me one single z. Here I send you, of course, f of so g of z, and h of z. Okay. Here is pf. I send you PG and PH. Okay, so you know that these evaluations are here. Okay, and here the idea is we can check that this constraint, these relationships fits at z, and if z is enoughly high, I mean, if it's a small, you can trick that. But if z is a big number, okay, then I can. So I proving just one single point, I can prove that the full polynomial is the same. And this is, I mean, this is a fundamental part of this. So here is with a single check in a single point, I'm just checking all the polynomials. So I'm just checking the relationships. I'm just checking like a lot of things in parallel.
This is, as you said, the fundamental part of the case. This is because the polynomial degrees are relatively low compared to the size of the field. So if you randomly choose like a point in the field and they actually hold, that means like with extremely high probability the equation actually.
But this is, I mean, this is fundamental because I mean this polynomial can be of degree 1 million or 10 millions. So then I'm checking at the time in parallel. It's just a single polynomial commitment. I'm just checking 1 million or 2 million constraints at a time. Okay? So this is the main trigger of all this. There is another important thing here that's important to know. This is an interactive protocol. Okay, so here you need Peggy and Victor, but actually you want to convert this to what we call it a non-interactive. I want to generate a proof that I commit this and I just generate the proof. Here there is one trick, is the Fiat-Shamir heuristic. But the idea is, okay, so here we don't have verifier. So we compute Z as the hash of the transcript, I mean of the hash of all these commitments. We set the commitments, then we compute the hash. Because hash is not reversible, we don't control. So Peggy cannot control Z. So this is like kind of a random. So, and I mean, there is a full mathematical theory behind that, but this is the idea. So we can convert any interactive protocol to a non-interactive. So generating a proof where there are some polynomials, relationships, you can commit to some polynomials and then you prove that those polynomials, these commitment polynomials, fulfill a specific relationship of polynomials. Okay, and this is very powerful. Okay, but next question that comes is, okay, this is cool, but we have a problem here. That's a state machine. So how we convert that from here to here? Okay, so let's try to connect this problem in a polynomial constraints thing. So I clean it a little bit. So let me see how I clean it. I keep the, well, here is, well, you see that there. So I clean it everything. Okay. Okay, let me just start. Let's write the state machine. Okay, so here is a, let's do it with 8 times. Okay, this is A, this is B. Okay, let's start with 2 numbers. Let's start with 1 and 2. Okay, so then A is 1, so this is 3, and B is first. Just here 1, 2, 3. Let me put 2 here. just to be more clear.
Okay.
Okay, so the 3 goes here,
Yep.
and here I'm just starting 5. Okay,
Yep.
so here is 5, 8,
Yep.
here is 8, 13, this is 21,
No, that's 13. Yeah, that's
21, this is 30, no, 21, 34, and this is going to be
34?
55, no, well, 34,
34, yeah.
4, 55,
55,
okay, that would be the same machine,
Yeah.
okay? So, imagine that this is, so this, let me just put it in red, okay? So here, what I have here actually is, we have 2 polynomials, okay? This is one polynomial, this is polynomial a of x,
Yep.
okay? And this is polynomial b of x.
Yep.
Okay? Yep. So what's this polynomial? Well, just a polynomial of degree 7.
Yep.
Okay? Where it evaluates to these places. Where we need to pick up a point to evaluate. Okay?
Right.
So here is, I can choose any of those. So any of those work. Okay? But there are ones that are very, very, very useful.
Yes.
Okay? The ones that we are using is the one that are what we call it the roots of unity. Roots of unity, I mean, it's the roots of unity. You know, the root of, if you go to the complex, for example, the root of, so the square root of 1 is 1 minus 1. If you do a square, the cubic is square, so the 3 square, the 3 root of 1 is actually is one of those. It's always, but it's going to be also 2 complex numbers. I mean, if you go to the complex, here you have the circle unit. So if you just divide the circle in these are the roots 3. Okay, if you want to do the roots 9, I just divide this circle in 9 in 9 equal parts, and here you will have the 9 roots. Okay, so these are the roots of unity. Okay. Here we are in finite fields, but if the final field is certain way, you also have these roots of unity, but the roots of unity are going to be certain numbers. Okay, so there's numbers that when you, I mean, if it's a square fourth, and when you multiply that number 4 times, it will at the end will give you 1. Okay, but they are going to be concrete. So these numbers, if the final field exists, if the final field is well, has a good duality. That's what we have actually. If pi actually is if pi minus 1, so pi is a prime field. If pi minus 1 is multiple, is something like 2 to the 28 times c, that means that you will have 2 to the 28 roots
of
unity. Okay, so that's 2 to the 28, 2 to the 27, 2 to the 27. You have square roots, so square. Okay, so you have all of them. Okay, so if the prime is good defined, and we are working with primes that are well defined, this fulfills. Okay, and here, so the idea is that, well, these roots of unity we can express them. In this case, we need the xth root of unity. Okay, so that these square roots, I mean, it works the same. I mean, having 1, imagine that we have 1. So here, I can convert. I know all the xth. So if I have 1 primitive, I can have all of them. So I can get 1 to 0, 1 to 1, y to 2, y to 3, y to 4, y to 5, 6, over to 7. Actually, w to 8 is a square 8th root, so it's going to be 1, and w to 0 is something to 0 is 1. So it's a circle. You see, it's a circle itself. Okay. So here we have, of course, that f of w0 is equal to f of w1. Well, in this case, is a. A of a is 1. A of w2 is 5. Okay, and the same thing here.
Yep.
Okay, b 0 equals 1, b w1 equals 2, and so on.
Yep.
Okay.
Yep.
These are the evaluations. Okay. The cool thing is that, for example, for converting 2 evaluations to coefficients, here I can apply one thing that's called the FFT, and I can go back and forth super fast. Okay, so I can go to coefficients and so on. Okay, so what I would do? Okay, so here I have the polynomials. Okay, and what's the relationship that needs to follow? So how can I convert this to some relationship? Okay, well, the relationship here is, well, here is a plus 1. Okay, so if here is, if a is f of, here you see that a of, okay, so here, let me put here. So here is that would be a of wx equal a of x plus b of x. Okay, and b of wx, see here is that wx is the next one.
The next
okay?
one, yep.
Of course, here we have the problem of the last one. Okay, we'll solve it now. Okay,
Yeah.
but here b of x is equal to a of x.
Yep.
Okay. Yeah. Let's solve this problem, because I mean, okay, this works, but of course you see that this relationship will fill everywhere, but the last one,
the last one doesn't work.
that doesn't work.
Yeah.
Okay. So here what we can do is we can define another polynomial. We call it a constant polynomial. So it's a polynomial that this is a trace. I mean, this is depending of the numbers, it changes, but there is another, but it's
constant doesn't.
yeah. So here is, we are going to define one polynomial. Let's put a polynomial where here is going to be 1, 0, 0, 0, 0, 0, 0, 0. This is actually the Lagrange polynomial. Is the basis. Is the this we call it L1 of x. Okay. So this is L1. Okay. So what I'm doing, okay, I want to convert. So this needs these equations needs to apply, but only when L1 is 0. Okay, not when L1 is 1. So one thing that I can do is, well, I can, I'm gonna reconvert this. So I'm converting this is equal to 0. Okay, this equals to 0. Okay, and I want this to happen. So what I'm gonna do is I'm gonna multiply that. We'll multiply that. I'm gonna multiply that by L1. Actually, it's 1 minus L1. Okay, and this equals to 0, and all this 1 minus L1 fix equals.
Right.
Okay.
Yep.
So you see here that, well, of course, if L1 is 0, this is this condition must fulfill. This is in, everywhere. Okay, so this is everywhere. But in the first one,
it's 0. Yeah.
Yeah. Actually, this is wrong. Well, let's put here. So actually, the last one is the one that's not defined. Okay. So it's in the last step. So the next in the last step is the one. Okay, but okay, this is L8. Right, L8. Yeah. So here is L8. L8. Okay, just to be precise on that. Okay, but okay. So we already have a polynomial. We have two polynomials. We have a constraint. These polynomials we call it the trace polynomials. Okay, because actually this is L is we call it a constant polynomial. Okay, but constant is known by the prover and the verifier, and then I do exactly the same. So how the protocol would work? Well, have again Peggy and Victor. In the first, I would commit to A of x and commit to B of x. Okay, Victor would send Z. Okay, here I would send. So Peggy would send A of Z, B of Z, and its proof. Yeah.
Yep.
And Victor would check this. I mean, we check these equations by just substituting x with Z. Actually, you see here that, well, here is Wx. So actually here, I need, for these equations, I need A of x, so in this case, A of Z. But here I would need also A of Wz. So I need this opening too. So,
right.
And P A W and B of Wz. Okay. Here will be P of BW. Okay. Well, no problem. Instead of doing one opening, I'm doing two openings. Okay. And then I'm just checking, just substituting these values with these equations, and I mean the prime field is not field. Of course, I can convert that to field Shamir. So I can generate a proof. So here you see that I generated a proof for that. Okay. Here another important part is, okay, but here is, I mean, you are proving here that for any value, but I want to force here, the prover wants to, the verifier wants to force, for example, the input. Okay. So how would you force the input? Well, you see here, well, here the verifier would need also the evaluation of LA to fx, but LA of x is a constant polynomial, so he knows how to evaluate that. Okay, but so imagine that this is what we call it the public inputs in this case, so public inputs of polynomial. So I want to force public inputs. This is something that the verifier have, okay, but you want to prove that those values are correct. Okay, and the idea is that you do this by adding another constraint. In this case, it would be L1. Well, here I'm using L8, but imagine that here is L1. Here I want to prove that in L1. So when L1, or if you want L8 WX, which is L1, okay, because it's the next value, okay, times, and here is A of x minus, and here is the let's say A0 equals 0, and then here I can do the same. This is L1, this is the first line, okay, B of x minus B0 equals 0. Here you see that we extended, so this is, but then again, it's you do the same, you commit to A of x and B of x, here you sense it. Of course, here you will need these values in order to evaluate these values. A0 and B0 are public inputs, so you want to, the verifier, this will be part of the verifier proof, so they will be known by the verifier, and they will check that A of x minus 0 at A of z, so actually you will check that L1 of zW, so L1 is well, L8 of z. L8 is known, okay, it's a known polynomial, times A of z, this was sent by the prover, and be sure that's correct, meaning so A0, which is the public input, is equal to 0. Okay, so you see here that, I mean, this is the kind of for public input, but here we converted a state transition function, you see this is a state machine, state transition function, to a polynomial problem, and using the polynomial commitment schemas. There is a lot of ways of doing this polynomial commitment schemas. You can understand this as a black box. Okay, and so we are able to get, I mean, we can prove, if you have a state machine, I mean, it's like we have a clock, okay, so we have these state transition functions, we can prove this in parallel, so we can build processors out of that, okay, so that's this is the basic, the core, the basic part, and from here we can start talking about other things.
Okay. Actually, one quick question. Usually in practice, how are the constant polynomials communicated to the verifiers?
Here, well, I mean, no, the constant polynomials, they are like part of the circuit. I mean, they are defined. So when you design a circuit, here I designed the circuit, and here I designed that should be a constant polynomial that should have exactly these values. So there is, I mean, so this is, theoretically, you don't need to do anything else. I mean, the verifier knows these polynomials. The thing is that a lot of times, I mean, you can have a lot of these constant polynomials. And in order to reduce the memory of the verifier and the complexity, sometimes what you do is, instead of the verifier having to compute the evaluations, the idea is we can have like these polynomials like pre-committed. We have a commitment of these, like if you send these polynomials, but they are pre-committed, so you can generate in the setup phase, okay? And then what you can do is here you can send the openings with the proof itself. So here, I mean, I would have, the verifier would have just a commitment of L8 of x. Okay, this is computed in the setup phase. Okay, and here you would just send here L8 of z and a proof PLL8.
Yep.
Okay. This is sometimes is more practical. Okay. So this is instead of having the verifier to compute. Okay, let the prover to compute it and prove it. And you in general these protocols here I'm sending a lot of proofs. Here we can aggregate all these proofs in a single one. And I mean the mechanisms for doing this in a more efficient way. There is things, but essentially what you are doing is very much this. Okay.
Okay. Yeah. Sounds good.
So this is, I mean, this is the, we'd say the basic of the, but this is the core part. I mean, is the basic. There are some other primitives that are relevant, that are important. There are, for example, the permutation checks and the lookups, which are important pieces. So here is, for example, I can have like two polynomials. Imagine that, well, here's two polynomials. And, well, imagine that you have a polynomial that's 1, 3, 4, 8, 4, 4, 5. 5, okay? And you want to check that this is, for example, is in 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this would be a kind of a range check. Okay, so here you can, there are some, you can express this kind of relationships that, I mean, the numbers of these polynomials must be included in this polynomial, or it's just a permutation check. Okay, imagine that here have a polynomial is 1, 2, 3, and here have 3, 4, 5, 6, 7, 8, 2, 1. Okay, so this is a permutation of the other. You can express this kind of relationships with some mathematical expressions. If you are interested here, you can check the lookup arguments and I mean, there is a lot of literature talking about that. But these are very useful because, for example, a permutation check allows you to have like specialized state machines. Okay, I can have like a main processor state machine, but then I can have, for example, a arithmetic state machine or a binary state machine or a Ketchak state machine. So there are some state machines that act like very much like a coprocessor. So they are state machines that are doing specific operations. And then I can link them on each other just by a permutation check. I mean, I'm just checking what's here is also there. So what I'm assuming that's correct in this state machine, it's actually proven
in that state machine.
In that side. Okay? I mean, how you solve memory. I mean, there is a lot of things. But I mean, see a processor, how it works. I mean, it's just a normal processor with instructions, with conditional jumps, with we got memory. Actually, we got a ROM. A ROM is the program that's executed in this processor. And and with that is, I mean, if you see the zkEVM, at the end is this processor with this ROM, and this ROM is a code that actually is like a geth. I mean, it's just
actually, Jordi, do you want to draw the architecture of like how the zkEVM like processors actually, like the main state machine and the other different state machines?
Here is, well, we have a, well, it's not, I mean, it's not very different than what would be a normal. So here we have a main state machine. The main state machine, there are two processors that they are tied very much together. One is, we call it the ROM. The ROM is not driven the state machine. It's just our polynomials that represents the program. Okay, and then we have the memory. This is like the core part. And then there are auxiliary state machines. Here we have the most important part are, let's say, the binary. Binary state machines are doing things like addition, subtraction, XOR, and ORs. I mean, binary things, and I mean things that are byte to byte, bit to bit operations. We have the arithmetic. Arithmetic state machine is mainly for multiplications. 32 bits. I mean, 256-bit arithmetic. So it's doing a 256 bits multiplication in a different prime field. This has some complexity. There is a state machine that's mainly doing that. Here, but we have others. Here we have another that's storage. For example, for the storage, we're using a sparse Merkle tree. It's kind of a Patricia trie, but much simple. Binary, just but have a storage. We have here we have arithmetic storage Ketchaks, for example. or SHA-256 now, and some other, I would say, some other very specific made. For example, we have, but these are more EVM expected. For example, we have one to deal with unalignments in memory. For example, in the EVM, for example, there is a problem with, I mean, you have words of 256 bits, but you actually, when you are, the memory is byte aligned, so you can do things like that. So, I mean, we could do that in a very, with binaries and arithmetics, but, but this is used so many times that we have like a specific arithmetic, a specific state machine to split and divide, I mean, to join, to deal with that specific, with that specific cases, okay? But this is very much I mean, the architecture is just different state machines, and developers don't need to worry very much about that.
And do you also want to talk a bit about zkEVM, like the assembly language you developed for the zk process?
Here the idea is we built, so one of the, in order to build this arithmetization, I mean, we see these polynomial things. Actually, we built one language to deal with, I mean, to create this, and one language and a tooling for, we call it this arithmetization, for creating these state machines. Okay, this is called PIL. Okay, it's polynomial identity language. It's just a language for defining that. We have also a lot of state machines already designed, like the arithmetic state machine and binary state machine, that they apply directly or with very small modifications to what would be a zkEVM state machine. So what we are doing is we are taking all the tech, all the work that's already in the zkEVM. We are adapting, if you want, changing small pieces, but the idea is just taking, and instead of having a EVM, we can have a WASM thing. Of course, the arithmetic, instead of being, for example, 256 bits, is going to be 64 bits operation. Okay, maybe Ketchak, you need it or not. Okay, so or maybe you will need some other. I mean, here we have the discussion, for example, if we were interested in floating points or not. Okay, but this is. But this is a hard one. But I mean, at the end, it would be another state machine. So here the idea is like a hardware design. I mean, you can have like different state machines, and then you can plug them together in a different way in order to build different. Of course, the ROM is going to be different because the program that you are going to run probably is going to be different. But the architecture is very much the same. So this is the work that we have been doing until now is just trying to see and adapting the current technology to do the zk zkEVM.
Maybe for people who don't like fully understand how this works in practice, like it might be helpful to talk about this entire execution trace, right? So like on the one side you have this like rows, like a lot of them. I think you have like 2 to the 23 that's limited today, and then on the other side,
you can change that, but this is what we're using.
And then on the other side you have all those like columns, and each column essentially represents some kind of like variables you're introducing in each of those like circuits, and then or like processors, and then eventually like you get like all those, the entire table filled with the execution trace, and then you kind of commit to that.
Yeah, I mean, each column is a polynomial, and then you commit to all of them. That's very much what you do. Here, I mean, there is a lot of things to talk about. I mean, but yeah, this is the main architecture. I think these are the main pieces, and with this you can have more or less an idea how everything works. Of course, there is the details where things get more complex, but this is very much the main idea.
Okay. Okay, maybe we can switch to talking a bit about how the zkEVM works on the high level, like from like a L2, like from a rollup point of view. I think so far we've been talking mostly about how it works from a zk or like a computation point of view, but there's still this part of like how it works is like L2 because it has the sequencer interaction with L1 and then all the like L1 to L2 messaging.
Yeah, at the end this is just full technology to prove. I mean, so how we see this prover at high level? I mean, the prover is okay. This is like a normal. I mean, you have a state root, Okay, you have a set of transactions.
Yep.
This is a state transition function. And okay, at the end is you have, so if you have this state root and you have these transactions, you get to this new state root.
Yep.
Okay, so here at the end, the prover altogether is at the end is a piece of code that okay, you give them this, this, and this, and it generates a proof that actually this is correct. I mean, you cannot generate a proof with a different state root than this other one. Okay? So this is the prover. So you can understand it as a black box that actually does that. Okay, but then you need to feed that in a system in a layer 2. Okay, so how the layer 2s work, and here, of course, there are different layer 2s and can be some details on the way. I'm going to explain very much how the Polygon zkEVM works, but it's not very different than how other layer 2s works. Okay, so the idea here is the best way to think about this. So we have a network, okay, that's running. Okay, so we have a state root, and sometimes it evolves. So some transactions are sent at the state root, but it's a different chain. I mean, it's not a Ethereum chain; it's a different chain. That's why it's a different network somehow. Okay, and here is when you want to submit something to the network. In general, the first thing you do is we call it the sequencer. Okay, the user just sends this to a sequencer. That's in this case, imagine that's a centralized sequencer. Okay, just a server that's getting the sequencer. Okay, the sequencer sequence that transactions. Actually, sequencer is building these blocks. Okay, so it's building a state. Actually, it's building here the transactions. It's putting all these transactions: transaction 1, transaction 2, transaction 3, transaction 4. Okay. Maybe here have a new state. Here it can be a batch or different blocks, okay? But at the end, it's sequencing transactions. It's getting the transactions and putting them one after the other, okay? And if you trust the sequencer, you don't need anything else. I mean, the sequencer gives you, it's like a normal blockchain. It gives you a new state, the state is valid, okay? But of course, the sequencer can lie. And I mean, if you want to build that, you go to a bank. I think it's that makes no sense. Okay, so the sequencer, what it does is once in a while, maybe when it gets maybe a bunch of transactions or after a timeout, okay, it sends this information, okay, to the mainnet, to the L1. Okay, just take and it's just sequencing, and here this is the L1. Okay, and actually with this step, so they don't tell which is the new state. It just put the transactions. Actually, it just take the transactions and they put them there. Okay. So at this point, the transactions are final. I mean, these are committed. Anybody. So the thing is that the blockchain doesn't know what's the current state. But they know that the transactions are going to be executed with this order, and because this state transition function is deterministic, and one property that maybe I don't mention, that all the transactions are valid or are executable. Maybe they are not valid, but imagine that a not valid transaction is just an operation transaction. It just don't modify the state. Okay, but I mean, so you deterministically, when you have a set of transactions, you have a state, you have a set of transactions, you deterministically you compute what's the new state. So at this point, without generating any proof yet, just putting the transactions, here we already have a blockchain. Okay? The problem of that is that the people needs to, well, there are many problems with this. Okay? So one problem is that people needs to follow the full chain. I mean, it needs to compute the chain from the beginning if you want to know the current state. And the other problem is that, imagine this is an L2, okay? So when you want to withdraw funds, you have to withdraw funds, okay, the folks are stuck in the L1. So how the L1 knows that this state is actually
valid?
You're valid and you can withdraw funds, okay? So here there is another process, different actor in parallel. We call it the aggregator. That actually is seeing what's in L1, I mean, everything that's committed, and they are generating these proofs. So they are generating the proof, computing the new state, and generating the proof that this state is actually this one. Okay, so here we call it an implicit state. It's a state that's it's known, but it's not on blockchain. But this guy is, because the proof is sending the new state, here you are sending the state, and with the proof, and this proof is verified on chain, so you know that this state is correct. And it's at this point where you can withdraw the funds, because you already know the state. This state can include, so what exits you can do. So you can, at this point, for you can exit. Okay. So this is this explicit state. This is the prover. Okay, and this is important for withdrawing the funds. For example, in optimistic rollups, this stage is much longer.
Here is 7 days.
Process. Well, because it's a process for. I mean, it's a gaming process. I mean, it's a challenge process, and then you need to give time for others to prove. We call this is the
challenge period.
Yeah, it's a challenge period that you need to deal with. Okay, but in a zk rollup, this time is the time. So it just generate the proof, and that's it. You know, if the proof is well generated and the proof system is correct, you know that this state is correct, so you don't need to wait anything more. This is the big difference between one or the other, and this transition period. So there are some details on the bridge. I mean, because the idea of the layer 1 and L2 is like you need to be able to transfer funds from L1 to L2 and transfer back. Okay, and here there is a mechanism, a special mechanism. It's a trustless bridge, so it's the kind of automatic. Okay, and some mechanism that happens here. Okay, so but
actually, how about we just talk about the bridge, because there needs to be like a mechanism to communicate between the L1 and L2. Like P1 needs to be able to deposit and then withdraw their funds back, and then maybe L2 also needs to read the L1 state and things like this.
Yeah, the idea. Let me explain you, give you the big picture of how it works. The idea is that when somebody wants to send funds to L2, okay, actually is here what you do is you send the funds to L1, you put it in you send the funds to some smart contract in L1, and this smart contract builds what we call it is a global exit tree. But in any case here, what you do is this is built in a smart contract, and it's a append-only tree. It's very much like when you are depositing something for staking in Ethereum. You're just sending funds there, and you build the Merkle tree of all the funds that are set there. Okay, and one leaf for each deposit. Okay, so this global exit root at some point. Okay, so and this is part. I mean, when I pin the sequencer, at some point the sequencer, but in this sequence here, actually you are including the global exit tree and putting this global exit tree in the root, in the state tree of the L2. Okay? And this is done automatically in this mechanism. Actually, here is the sequencer can include this global exit tree whenever he wants. When you are doing this sequencer, you verify that what you are putting there is the correct one. And even more than that, I mean, the sequencer in this transaction, in the smart contract, it's forced that you include the root. Yeah, so this is very important for what we call it the forced transactions. But you are putting this, so you are sure that, I mean, if you are depositing here, this is going to be included in the state tree. So this global exit root, I mean, this root of all the deposits that you are doing, at some point this is going to be available in the L2s. This can go really fast because the sequencer don't even need. I mean, the only what they will do is they want that this is final. But once this is final, so they don't need to wait to approve. I mean, they can include quite fast. Okay, and once this global exit tree is in a smart contract in the L2. Then in the L2 what you do is a claim. A claim, I mean, it's in this smart contract in the L2, and here you can do, mainly what you do is, okay, you get the funds in L2. The ones, of course, they need to match in the exit tree, it needs to exist, and then, of course, you just check, I mean, you just mark that you cannot withdraw the funds twice. I mean, you just put that this leaf is already used, so you cannot use it again, okay? So this is how you transfer from L1 to L2, okay? And for the 2-to-1, the mechanism is very similar, but the other way around. I mean, in each state machine, we have like it's the local exit route, and it's for the exit. It's like so when you are in L2 now, and you want to withdraw the funds in L1. Actually, what you are doing is you are sending those funds to L1. So you are creating this tree in L2. This, you are putting a leaf in these L2s.
Yep.
There is a mechanism for synchronizing this root of the L2 to the L1.
To L1, yep.
And then in the L1 you do the same. I mean, you have this mechanism. You do withdraw. You prove that this leaf is in there, that you have not used that leaf before,
right.
and then you get the funds back.
Yep.
But the mechanism for updating the local exit route in L1, this happens in the prover, in the proof side. So you need to prove that actually this is the new state that includes this global exit route. Actually, I mean, to be more concrete, the prover that I mentioned here is state I. This is the output is a state I plus 1. Okay, here, okay, you are proving that go from one state to the state. Here we are also saying the local exit tree. So and this local exit tree is updated in the smart contract in L1. So every time that a proof is generated, that the proof is generated, we update the local exit tree. I mean all the exits of the L2. We update it in L1 so that we can withdraw that in L1. Here to mention that the proof, this proof is not one proof per batch. Okay, it's a proof that we can aggregate many proofs. So the idea is that we can have like 1,000 or 100 batch, and we aggregate that in a single proof. Okay. For example, I think we are sending now one proof every half an hour, and in half an hour maybe there is, I don't know, 1,000, 2,000, 10,000
transactions.
Batches.
Batches. Okay.
Yeah, batches, and each batch has a proof, and then we aggregate all the proofs in a single proof. This is the aggregation. The aggregation.
It's just mostly down to save on cost, so that
save
every half an hour.
Cost mainly, because I mean, but it's not the proving cost. It's the, I mean, if you have to send one transaction.
The cost verification on L1. Yeah, it's not cheap.
It's not the cost of verification, but it's even the cost of sending a transaction.
Sending
a transaction or updating all these routes and all that stuff, and it's called, and you pack all together. And, and this, you convert something that would be a variable cost with something that's just a fixed cost of the network. Well, in the Polygon, in the Polygon 2.0, the idea is not to have one single proof per chain of many batches, but have one single proof for all the chains of Polygon 2.0. There is an optional. I mean, if you are a chain, you want to generate your own proof, that's fine, but it's going to be a mechanism that with a single proof, we are able to verify all the chains at a time.
Okay, so like on the L1 to L2 interaction, how does forks on L1 handled? I assume, for example, on the sequencer side, when it needs to read L1 state, it needs to read the final state unless the sequencer itself has a way to revert when L1 reverts, right? So.
Well, here, what we're doing is that, I mean, the sequencer. So when you are sending this, when you are sending the sequencer here, it needs to be correct. So you cannot sequence something that you cannot sequence a global exit route that's not
final.
Not final. Well, this is L1, so you don't need to be final.
Right.
But the sequencer in general is going to wait for the finality in L1 because I mean if it changes, then all the state that needs
to revert as well.
It will need to revert in there. So it's more practical right now to just wait a couple of epochs in Ethereum, and you know that for sure that's final, and then you can.
And what about the L2 to L1?
Well, L2 to L1 is not much a problem because of the problem that you send the proof. So when you are sending the proof, you are already committing to there. So
it doesn't matter.
It doesn't matter. I mean, if you revert it, the proof will be reverted too. So I mean, and the withdrawals that you can be done later on will be reverted too. So it's not a problem on that side. But the sequencer here is finality in L1 is important for the deposits.
Makes sense. Okay, so given that we're kind of about to run out of time, is there anything, and we also cover both the kind of the rollup side as well as the zk side. Is there anything else you want to talk about? Maybe like the future of Polygon, zkEVM, or like how do you see this, or like how do you see this whole like thing, like including Polygon CDK evolving in the future?
Yeah, well, in Polygon, we are building this Polygon 2.0. This is what we call this constellation of rollups or chains of different, different chains.
Yep.
And the idea is that they can share the same liquidity, and because of this this single proof that somehow validates the chain of the full network, this can be seen very much like a clock. I mean, imagine that this proof happens every 30 seconds.
Yep.
So that means that if you have different chains, you can do it.
Right.
I mean, you can transfer from one side every 30 seconds. So you can see the full constellation of rollups. I mean, the full Polygon 2.0 as very much as a single chain. Here, I mean, interesting things that that NEAR you are doing are important. I mean, this inter-sharding communication, for example, is something that's a super interesting thing to look about, or even the data availability is also another point. I mean, here there is a lot of points of exploration that we can learn one each other.
What about on the zk side specifically? Where do you see the new breakthrough on the zk front?
Well, in the CDK, of course, for example, for us having zkEVM as an option for chains in the Polygon 2.0, this is this is very important. I think this is giving the options to the users, to the applications to develop in WASM, the SDK. This opens up the market for this. This is really important. But here, I mean, I would say I'm more worried in the short run. At this point, is we have right now a constellation with one single star, like the zkEVM. Now we need to put the next star, okay, and from here start growing. I mean, this is the plan for the next years, and here we'll start connecting all these things and see how the things are evolving. I mean, there is a lot of. You do the zkEVM, but then it's like you open a new world, and we are starting now. And
right.
That's very much where we are at the beginning of everything.
Cool, that's a very exciting future. And again, thanks Jordi for joining me for another episode of the Whiteboard session, and thanks everyone.
Okay, thank you.